What's up everyone, my name is Miles Radliff. Welcome back to another Fluent flow simulation. Today we're going to be doing a flow simulation that uses a flat plate at an angle of attack, 0, 30, 60, and 90 degrees. I've already completed a few of these, but we're going to go through and do the 30 degree together. So I'm going to take an opportunity to kind of talk through this a little bit with you guys. Grab the XY plane, grab a new sketch, change the units to centimeters, and we're going to do a 3-point rectangle. We're going to come over here, make our dimensions. Let's say 50 and 5 centimeters. We're going to add a few constraints, and then we're going to put our angle in. And that's the flat plate. So now we're going to create a domain. Come back here, we're going to grab some more dimensions. And there's going to be our domain. Let's go ahead and make this into a surface. And that's everything we need to do for the sketch. Now we can move on to the mesh. Here we are on the mesher. We're going to go through and do a few things the same, but a few things different. I'm going to create method. Grab this guy. I'm going to create refinement of the same guy. Come over here to my default mesh size. I'm going to make it 0.05. And I'm going to make my level of refinement 3. Before we go, I'm going to create my wall selections. Now that we're all named up, we're ready to move on to the solution set. Here we are in the setup. Let's grab a model. We are going to be working with K epsilon today. Enhanced wall treatment, pressurized gradient effects. That's good. Onto the materials, fluid, air. We want to make sure that our flow is turbulent, so we are going to say 1, and with the velocity that we're going to use, we're going to have a viscosity of 0.000005. On to the boundary conditions. Our inlet is going to be a velocity inlet. We're going to make it have a velocity of 5 meters per second. Our outlet is a pressure outlet. I'm just going to say prevent reverse flow. Symmetry should be symmetry, and all the walls should be walls. So we're done with that. Now we can move on to initialization, and we're going to run this calculation for 1,000 iterations. So the calculation is complete. We can move on to the results. Here's the results page, and it's pretty empty right now, so we're going to add some things of interest. We're going to add 2 contours. We're going to add a pressure contour. Looks about right. Now we can move to a new contour. Let's make a velocity contour. I'm going to make 1,000 gradients, or number of contours. I'm going to make that 1,000, and I'm going to make this velocity u. What I'm going to do is I'm going to create 2 more things. I'm going to create a vector field. I'm going to call it velocity 2. And there's our vector field. So what's important about this vector field is we've got all of these points where the velocity in the x direction is either going straight up, right here, all of these arrows are pointing straight up or down, and here the arrows are non-existent, which means air is at a standstill here, is stagnant. So we're going to create a polyline so that we can highlight those areas. 153 seems to be the sweet point, where you can see it's hugging the surface of the plate as closely as it can. And that should put everything at where the velocity in the x direction is 0. If I bring back my velocity vector, you can see obviously it's going to be 0 on the plate. But we can move in here and all these arrows are pointing with a velocity of 0. So that is how you can simulate an angle of attack on an airfoil to create a more efficient design. I hope that you enjoyed the video. Don't forget to like, comment, subscribe, and watch the video twice. I will see you in the next one.